Hello everyone, my name is Shruti Verma. I'm currently a civil engineering student at Faculty of Engineering and Technology, University of Lucknow. Today, I'm here to deliver a presentation on a very critical and often underestimated environmental issue, that is land subsidence. Here is a picture of land subsidence in Mexico. Before we dive into the details, let me walk you through the structure of today's presentation. We'll start with the introduction, then what is land subsidence and its type. Next, we'll discuss the causes and mechanism behind land subsidence. Then we'll explore its impacts and strategies to monitor and mitigate land subsidence. Finally, I'll conclude the presentation by discussing some case studies and sharing the references that support this presentation. Firstly, I would like to begin with an introduction to the topic land subsidence. It is a phenomena that affects both natural and human made environment. Its implications are far reaching and impact our daily lives in a way we might not even recognize. According to UNESCO, subsidence could affect 19% of the world's population by 2040. According to 2023 study, more than 6.3 million square kilometers of worldwide land is affected by land subsidence, which is about 5% of the total global land area, which is home to about 2 billion people, and that includes 231,000 square kilometers of urban area. This is a picture of land subsidence in Staffordshire, England, showing a house affected by subsidence due to 19th century mining, also known as Crooked House. Now let's take a look at what land subsidence is. Land subsidence is the gentle settling or rapid sinking of the discrete segments of the ground surface due to consolidation of sediments. It can be caused by both natural processes and human activities. Natural factors like dissolution of soluble bedrock can create a void that causes the ground above to sink. However, human activities significantly exacerbate the problem. There are many low-lying coastal cities around the world that are in the danger of inundating by the end of this century due to subsidence, and one such city is Jakarta, which is subsiding at a rate of 1 to 15 centimeter per year, and it can reach up to 25 centimeter per year at several locations. Now let's explore the types of land subsidence, starting with uniform subsidence. It is a type of land subsidence where the ground sinks evenly over a large area without creating significant cracks or fractures. It is often caused by large scale groundwater extraction, natural soil compaction, or sediment loading. It can lead to widespread impacts on infrastructure and landscape. This is a picture of subsidence in eastern part of Mexico City showing surface elevation in 1936 compared to that in 2013 using a groundwater well as a benchmark. The second type of land subsidence is localized subsidence. It refers to sinking or collapse of the earth's surface in a small specific area, often creating visible depressions, cracks, or sinkholes. Common causes include underground mining, poor compacted soil during construction, natural karst formations, or collapse of groundwater cavities due to water withdrawal. Its impacts are more concentrated. Unlike uniform subsidence, localized subsidence is concentrated in a specific region, making its impacts more immediate and dramatic. Here is a picture of sinkhole in Florida caused due to localized land subsidence, which was 16 feet wide and 19 feet deep. Now let's look at the third type of land subsidence, differential subsidence. It occurs when the ground sinks unevenly, creating variations in elevation over a region. It is often caused by variation in soil composition, differential loading from building, groundwater extraction, or geological faults beneath the surface. The uneven nature of differential subsidence makes it particularly dangerous, as it can lead to structural instability, posing safety risks and requiring engineering solution. A famous example is Leaning Tower of Pisa in Italy. Now let's analyze the causes of land subsidence. We can classify the causes of land subsidence into natural, human induced, and mixed causes. The natural causes include tectonic activity, volcanic activities, karst processes, erosion, and sediment compaction. The mixed causes include climatic changes and land use changes, whereas human induced causes include groundwater extraction, mining activities, oil and gas extraction, urbanization, and geothermal energy extraction. Here, a graph between relative frequency and influential factors indicates that human-induced causes are responsible for majority of land subsidence, with groundwater extraction accounting for the largest share. Out of all the cases of land subsidence around the world, 76.92% cases are only due to human-induced causes, of which 59.75% cases are due to groundwater extraction. Now let's understand the mechanism behind land subsidence. Since groundwater extraction is a major cause of land subsidence, the mechanism behind land subsidence phenomena caused by overexploitation of aquifers is based on the principle of effective stress, which states that when a saturated soil is subjected to total stress, this stress can be expressed as summation of effective stress and pore water pressure. A decrease in the pore water pressure and an increase in normal effective stress are the after effects of the incidence of excessive groundwater withdrawal from the aquifer system. The evolution of this process results in the compaction of the hydrostratigraphic units, which eventually leads to land subsidence. Here is a video illustrating how excessive groundwater extraction leads to land subsidence. When excessive amount of water is extracted from the aquifer below the ground, the clay between the pocket of water collapses and the ground starts to deflate like a leaky air mattress. This sinking is buckling the walls of irrigation canals, damaging the pipes and creating giant sinkholes. Now let's take a closer look at the impacts of land subsidence. Starting with hydrological impacts, these include groundwater depletion, increased flood risk, saltwater intrusion, and altered surface water flow. Moving ahead with geological impacts, these include increased seismic activities, alteration of geological features, surface cracking, and soil compaction. The environmental impacts include habitat loss, biodiversity decline, altered vegetation patterns, and water quality degradation, whereas economic impacts include infrastructure cost, damages of historical heritage, agricultural impact, and property value decline. Now let's examine some effective monitoring strategies, starting with INSAR, which is Interferometric Synthetic Aperture Radar. It uses radar images from satellite to detect ground movement. Its accuracy ranges within 1 to 10 mm. The advantage is that it has high spatial resolution, where disadvantage involves it is limited by radar signal resolution. The second technique is GPS, Global Positioning System. This technique utilizes satellite signals to measure precise positions of survey points. The accuracy ranges within 1 to 5 mm. The advantage is it has high precision capable of monitoring large areas over time, whereas disadvantage involves it requires clear sky visibility and it has equipment expensive. The third technique is leveling. It measures the difference in height between points using a leveling instrument. The accuracy ranges within 1 to 2 mm. It has high precision. The disadvantage is that it is labor intensive, limited to localized measurements, and require careful setup. The fourth technique is tilt meters. It measures change in the tilt of the ground surface to detect subsidence. The accuracy ranges within 0.1 to 1 mm. The advantage is it is highly sensitive to small changes, good for detecting localized subsidence, where the disadvantages involves it is limited to small areas and require frequent maintenance. The next technique is satellite imagery. It uses satellite images to analyze land surface changes. Its accuracy typically ranges within 1 to 30 meter and it depends on satellite resolution. The advantages are it covers large area and it is effective for long-term monitoring. The disadvantages are that image interpretation requires expertise and resolution limits. The next technique is aerial imagery. It involves capturing images from aircrafts or drones to monitor surface changes. Its accuracy ranges within zero point 0.1 to 1 meter. The advantages are it has high resolution, flexible coverage, and more detail than satellite imagery. The disadvantages includes it is weather dependent and limited flight time for drones. Now let's look into various strategies for mitigating land subsidence, starting with groundwater management. Groundwater management plays a crucial role in preventing land subsidence caused by excessive extraction. Sustainable practices such as controlled pumping and artificial recharge help maintain groundwater levels. The next is soil and surface management. Stabilizing soil through techniques like compaction or addition of stabilizers help prevent ground sinking. Also, vegetation with deep root system strengthens soil structure, reduces erosion and improves water retention, collectively reducing the impact of subsidence and enhancing land stability. The next is building regulations. Environmental impact assessment evaluates the potential effects of construction on the environment, while building codes ensure structures are designed to withstand ground movement. Stricter codes limit construction in subsidence prone areas, reducing risk to both building and infrastructures. The next technique is infrastructure reinforcement. Flexible materials adapt to shifting ground conditions while advanced monitoring systems track subsidence patterns. These systems provide real time data enabling early detection, accurate prediction, and informed decision making for effective land management and disaster prevention. Moving ahead to engineering solutions. Engineering solutions for land subsidence include soil stabilization, foundation reinforcement, and grouting. Techniques like micropiling and deep soil mixing strengthen sinking areas. The next is public awareness and education. Public awareness and education about land subsidence involve informing communities on its causes, risks, and preventive measures. Workshop, campaigns, and media outreach help promote preparedness and encourage sustainable practices to mitigate subsidence impacts. Now let's see the various case studies of land subsidence, starting with case study of land subsidence in Mexico City. Mexico City is built on the former bed of Lake Texcoco, which has soft compressible clay soils. In 1900s the rate of land subsidence was 8.89 cm per year, and in the late 1950s it was 28.9 cm per year. The primary causes are extensive groundwater extraction and urban infrastructure, which is adding weight to the ground. The impacts are infrastructure damage and increased flooding, whereas it also affects the economic cost related to repair and infrastructure adaptation. Here is a picture of a pendulum inside the Metropolitan Cathedral right on the main aisle in Mexico City. The pendulum shows how the foundations of the cathedral have been shifting since its conception. Now let's see the various mitigation measures adopted by Mexican government. First is regulation of groundwater extraction. The Mexico City water program introduced to reduce dependence on groundwater. The groundwater extraction has been reduced from 20 million to 12 million meter cubes per day since 1990s. The second program is water recharging projects, construction of infiltration wells and canals to divert rainwater into aquifer. Also, use of treated wastewater for aquifer recharge to restore water levels. The third is real-time monitoring. Collaboration between Mexican National Water Commission and UNAM, National Autonomous University of Mexico, to implement a real-time monitoring system to track land subsidence and collect data. The fourth is specialized foundation design for buildings. Use of flexible foundations to adapt to shifting ground. Then implementation of deep piling to secure buildings and prevent damage from ongoing subsidence. The current status of land subsidence in Mexico is the Mexico City is still sinking at an average of 50 cm per year. Since the beginning of 20th century, some areas have sunken up to 9 meters, that is 30 feet. Now let's see a case study of land subsidence in Jakarta, Indonesia. Jakarta is located on a low-lying delta region with soft alluvial soil. The rate of land subsidence in Jakarta in 1992 till 1991 was 3 to 7 cm per year. From 1991 till 1997 the subsidence was 160 cm, and from 1997 till 2010 the subsidence rate ranged from 1 to 28 cm per year. The primary causes are groundwater extraction and natural soil compression, also rapid urbanization. The various impacts are infrastructure damage and economic cost, also flooding due to lowered ground levels and compromised drainage system. Here is a GPS monitoring data which shows how much land subsidence has taken in Jakarta since 1997 till 2005. Now let's see the various measures taken by Indonesian government to mitigate land subsidence. First is limiting groundwater extraction, ensuring a stable and adequate supply of raw water sourced from rivers, lakes or reservoirs, also encouraging recycled water use. Second is taxing groundwater consumption. About 145 billion rupiah was collected by Indonesian government in the year 2018 by taxing groundwater consumption. Also developing water retention basins and building absorption wells, also known as biopores, to store rainwater to mitigate flooding and recharge groundwater. South Jakarta has 1250 absorption wells. Also encouraging lighter construction and honeycomb structure in buildings, incorporation of materials such as gypsum, bamboo, carbon fibers in building design. The current status of land subsidence in Jakarta is it's still experiencing land subsidence. Nearly half of the city is below sea level. Subsidence rate is generally 1 to 15 cm per year, but can reach up to 20 to 28 cm per year in some areas and at some times. Now let's see a case study of land subsidence in Joshimath, India. Joshimath is located in Chamoli district of Uttarakhand. The town is situated on a geological formation with a mix of loose, unconsolidated sediments and rock formations typically of the Himalayan region. The satellite data from July 2020 to March 2022 showed the rate of subsidence was 6.5 cm per year. The primary causes were natural as well as human induced. Natural causes includes seismic activities and geological composition, whereas human induced causes include unplanned development, hydraulic projects, deforestation and inadequate drainage. The various impacts were infrastructure damage, increased erosion, altered water flow and impact on local flora and fauna. Here is a picture that represents the crack appeared at an indoor badminton court in Joshimath area of Chamoli district. About 25% of the Joshimath town has been affected by land subsidence. Now let's see the various measures taken by the state government and central government to mitigate land subsidence in Joshimath. First, halt construction. The state government has stopped construction of the NTPC hydropower plant and the Hilang bypass. Second, evacuation plan. 30 families have shifted to rented accommodations while 902 people remain in the relief centers. Third, prefabricated homes. The state government has ordered 4,000 prefabricated homes. Fourth, seismic observation systems. The state government has set up micro seismic observation systems. Fifth, the government has declared Joshimath town a land subsidence zone. The current status of land subsidence in Joshimath is as of April 2024, the land subsidence in Joshimath continues with cracks widening and appearing in new places. The government has proposed building security walls and drainage systems, but no work has started yet. The references supporting this topic are as follows. Thank you.